Hey folks, in this video lecture we are going to be talking about the concept of regression. So you should have already watched all of the videos on correlation, so you know how we relate two variables to one another to see whether or not one tends in one direction as the other tends in a particular direction, right? Whether they're going in lockstep together, a positive correlation, or whether they're going in opposite directions, a negative correlation. We then talked about how you could potentially draw a sort of line through that cloud of dots in the scatter plot and use that line to predict sections of that graph that didn't have any dots in it yet. Essentially saying, if this is the relationship, then what would be the case if we had this value of x or this value of y? Well, that fundamental concept is regression. And so in this first video, I'm going to talk about how regression works, what it is we're going to be studying, a couple of little principles about regression that we should keep in mind, like regression to the mean. And then in subsequent videos, I'll show you how to calculate it, and then we'll go through a full-fledged example starting with just raw data and looking at correlation to regression until we're finally done and have calculated everything. Okay, so let's get started. Like I said, if correlation is finding relationships, then regression is prediction, right? It's that ability to look into that crystal ball and say, if these two things are related, then it's really likely the case that this is going to happen. And it's essentially how a lot of these psychics probably do what they do. It's unlikely that many of them have any special power, but instead are likely to see particular likelihoods based on some information they can get from you. Perhaps the way you dress, some questions, and the way you answer those questions ahead of time. It's the same kind of thing that your car insurance company does, right? They ask you a number of questions before they give you insurance. They might ask you, of course, about your vehicle, right? So what kind of vehicle do you drive? You know what kinds of vehicles tend to be the higher insure rates? Sports cars, right? Especially convertible sports cars. They're going to ask you about your gender, your age, your driving history. So when I had a Ford Mustang convertible at one time in my life, I was also young, I am male, and I had one or two speeding tickets previously. So not a bad driving history, but that combination of variables the insurance company looks at in their database, looks at all those correlations, looks at partial correlations, puts them together into a sort of giant correlation and says, okay, now can we predict what's the likelihood that this individual, based on what we know and these correlations, is going to get into an accident and going to then file an insurance claim? Well, based on those particular variables, they calculated fairly high probability of me filing an insurance claim. Now, they were wrong. I never got in an accident in that car at all. But because of that, their regression line predicted high cost to the company. So guess what they did to me? They had high premiums for my insurance rate, right? And they're using regression equations, right? This is used in investing all the time. Now, I've got this old slide up here about the World Health Organization and avian flu. What do you think they're using right now to predict the pandemic? When you hear a new report that this particular model out of, say, Washington University or somewhere else says that we think there will be this many deaths as a result of COVID-19 by this particular date or by this later date. Well, they're using correlations that they see between, say, mask adherence in an area, already prevalent strains and rates in those areas, whether or not particular other things are being done like schools or restaurants are being closed. They know what each of these looks like because they know the correlation between each of these variables and their outcome, right? The spread of this particular disease, the deaths that they're trying to predict here, right? And because of all those correlations, they form a regression equation, which is just a linear equation, and it predicts what we're going to see at a particular date and time in this particular instance here, right? So regression is used all over the place. It's almost probably the most used, along with correlation, of any of the statistics that we have out there, except for, of course, the mean and standard deviation, those sort of little ones there. These are used in industry all the time. There's a high likelihood that whatever job you end up in, you might be using correlation or regression in some way. So pay careful attention, right? Now, it's important to note that we are going to be talking about what's called simple linear regression. Okay, you can have crazy shaped lines. You probably remember back in geometry when you saw parabolic lines, right? These ones that went woo, then came back down, kind of like this sort of upside down U, or maybe it looked like a U. Right? Those equations were more complex, right? It wasn't the normal linear equation that you and I are used to. I'll show you that in just a second. We are going to use that simple, easy linear equation, right? The basic, we predict y because we know x, and we know the slope, and we know the y-intercept of that line, right? Using a straight line, as long as we know one, either x or y, we can figure out the other one, right? Because that line is just going to continue passing, and I can say, okay, carry it all the way out to the x, take my ruler up and see where it crosses, then go all the way over here to the y-axis and see what that value is, right? I can also do it using the linear equation, right? You guys remember this. Y equals mx plus b. Right? Very, very familiar linear equation, but I'm going to refresh it for you anyway. Remember, m is the slope. Slope is the angle of the line. It's often referred to as calculated by rise over run. If you don't remember what that means, rise being the vertical change in the line as a function of how far it goes over on the horizontal axis, right? Or what should be, we should actually say change in y over change in x. I'm gonna have to fix that slide here. It says change in y on the numerator, right? So how far does it change from one spot of the y-axis to the other spot of the y-axis? Does it go 4 up? Does it go 2 up? Does it go down, right? We calculate that. And then we do the same thing on the bottom, the change in x, right? And see how far it goes over to the left or to the right. Calculate that. That is our slope, right? It's really easy stuff. We've done it a million times back in high school, right? The y-intercept, that's just where the line crosses the y-axis, right? Where it intercepts the y-axis. Now, another way of saying that is y-intercept is the value of y when x is 0. Because if you look at where the y-axis is, that is right there at the center of the x-axis, right at when x is 0. So when x is 0, where's the line? Is it up here? Is it down here? Is it right at the center and also at 0? Right, so we can calculate that. We've done it before, so let's see how we might do it. I'm going to just put a hypothetical y-intercept and slope in here, okay? So let's say the slope was 2 and the y-intercept was 1. What would that mean? Well, it means it's going to cross the y-axis at that value of 1. It's also going to go up 2 for every 1 block it goes over. So you get a line that looks like this, right? It crosses right there at 1. It also goes up 2 and over 1. Pretty easy, okay? So now we can also use the equation to make a prediction. So what would y be if x was equal to 3? Well, that's easy. You've done algebra before. You just plug in the 3 here, right? So we just say y equals 2x plus 1. X is now equal to 3. So y equals 2 times 3 plus 1. Simple math. 2 times 3 is 6 plus 1. We get y is equal to 7. You can also see that on the actual graph, right? If you carry over to the x marked 3 spot and then go all the way up, you'll see that it crosses right there at the coordinates that we would call 3, 7, right? I don't know why it says 4, 7. Geez, there's typos all over this damn slide. All right, I'll have to fix both of those things. But 3, 7 is the coordinate space that you get because you put in a 3, you solve the equation, you got a 7. We see that on the line. This is all a refresher, just with a couple of minor errors, it seems. But this should all be familiar to you, right? Y equals mx plus b, plotting lines on graphs, entering values of x, solving for y. Very simplistic stuff that you've done a million times. That's really all regression is. So that's what we're going to end up doing now. So before we actually get into the nitty-gritty of the equation itself, let me sort of introduce how we're going to do it. So at the beginning of the correlation coefficient lecture, we introduced the concept called standardized scores. And look for an announcement related to that, related to your first exam. There's an opportunity to gain a few extra points on your exam. Linear regression using z-scores. The way in which we are going to create our regression equation is by using standardized scores. Okay, so if we go back to the data we used in our correlation, we talked about number of absences and mean exam grade. So a student comes and says, I'm going to miss 8 days, or I'm going to miss 7 days, or I'm going to miss 6 days, or whatever it is they think they're going to unfortunately miss this particular semester. What am I able to tell them about their probable exam grade? Well, we have a correlation coefficient, right? We calculated for that. It was negative 0.85. So we know it's negatively correlated. As absences increase, exam grades tend to decrease. And it's a fairly strong correlation at negative 0.85. That's not far off of 1. So I guess one way I could answer this student, the easy way of answering this student, is just to look at the average exam grade, right? Figure it out and say, the average exam grade was a 76, so you'll probably get a 76. That's not really tailored to this student's information, though, right? That's just me saying, what is the likely exam grade that anybody in the class would get, regardless of the absences? That doesn't take in that information into that prediction. So another way of potentially giving them a more accurate prediction of their exam grade would be to first use the relationship I know. Use what I know about absences and how that's related to exam grades, and then say, okay, how many did you say you were likely to get? Based on what I've seen in the past, you're likely to fall about here and thus get a 62 or an 82 or whatever the prediction happens to be. Okay, so that's what we're going to do with these data, and we're going to do it using z-scores. So I got to show you a new formula, right? Now, remember, just as I've said before with correlation, there are multiple ways to skin a cat in this case. There's multiple ways of finding your regression equation. There's multiple ways of creating your correlation coefficient. We are going to use this method so that we are all on the same page. It makes it easier for you to do, for me to grade, for you guys to work together to figure out how to help one another. It's somewhat reciprocal in that sense. Okay, so here's our formula. We have z of y, and y's got a little hat on it. In fact, it's called y hat. We'll get to what that is equal to the correlation coefficient. The only reason I put xy as subscripts there was just to remind you that that was the correlation of the x and y variables. Okay, so I'm putting a lot of subscripts on here, really just to be extremely specific about which things I'm calculating and which values I'm using. So you see the correlation coefficient is then multiplied by the z of some x. Okay, so let's break that all back down. Go to the front. We have z of y hat. Y hat is the predicted score on variable y. So you go back to our linear equation before, and I said x is equal to 3, and then we solved through. That y that we got of 7, that would be a predicted score of y when x was equal to 3. So this z-score at the beginning of this equation is the z-score of a predicted y-score. Okay, so we need to get a predicted y-score. We also, it looks like, need to find a z of a particular x-score. And so if we want to find z of a y prediction, we take the z of an x-score and we multiply it times our correlation coefficient. Now remember, we can get z-scores from raw scores as long as we know the mean and the standard deviation of that population, right? So it's easy. We would just basically have to take a score, use the mean and standard deviation of the population, and get a z of x. Multiply that times our correlation coefficient, and now we have a z of y. Then we just use our z-score equations in reverse and take them back from a z to a raw score of an x or a y, and all of a sudden we've got our x and y coordinates. Okay, that probably seems a little confusing at the moment, but trust me, it is extremely simple. You've done z-scores, you've already calculated the correlation coefficient at this point, either because you did it in the last lecture or because you've done it earlier in the problem that you're working on. The regression equation is the simple part, right? It's about 5-6 steps perhaps, and then you're done. Okay, just again, you don't have to use these subscripts in every case. You're not going to see them sometimes if you look in the textbook. They won't always use these subscripts, especially the one for the correlation coefficient. I'm going to try and use them as frequently and consistently as possible, just to keep us all on the same page as to which z-score we're referring to. Is it of the x data or is it of the y data? Is this a correlation between x and y, or is it some other information that we're using? So I'm going to keep using the subscripts. Hopefully those will be more helpful than they are harmful for you. Okay, one last thing I want to point out in this video is a concept called regression to the mean. So when we use this method and we make predictions, we often see that if we take a z-score of the x variable first, right, because we're going to use that in that equation to get a predicted score, you see, in this particular case, if we were to take a raw score, x, plug it in with the information we knew about the population and standard deviation, and get that z-score for where that x sits in that distribution, we would get a negative 2.0 for that particular one. If we plug that into our equation and we get a predicted score for y, notice that it is only 1.7. That means that the x score was 2 standard deviations from the mean, but the predicted y score was only 1.7 from the mean. And if you look, you'll see in every case, the z-score for the raw data is always farther from the mean than the predicted value. Predicted values always regress back toward the mean. That's a concept that Galton and a number of others talked about, basically saying that over time, extreme cases, because they are extreme and not the norm, will begin to regress, begin to get closer and closer and closer to that center point, whatever the true center point or average is of that distribution. It's something that actually a number of people have sort of wrestled with, not realizing that regression to the mean was occurring around them. So there's a famous cognitive psychologist named Daniel Kahneman. He actually won a Nobel Prize for some of his work with Amos Tversky on basically behavioral economics. But in this particular case, he was working at the Hebrew University of Jerusalem, and he had Air Force, essentially Air Force pilot instructors. So the individuals who taught pilots how to fly these jets. They were in a class that Kahneman was teaching, and they began a sort of casual discussion, and he had been teaching about reward and punishment and these basic principles of operant conditioning, and how if you reward somebody or reinforce a behavior, it'll increase in frequency, and if you punish it, it'll decrease in frequency. And one of the teachers, the pilot teachers, raised his hand or her hand and said, I don't see the same thing in what I do around me. So, for example, let's say I have a pilot who goes out one day and flies a terrible performance, an absolutely terrible performance. Now, if I punish right then, and I come out and I yell, I say, rah, 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 you shouldn't have done that. That was really terrible. I can't believe you were so terrible at that. They tend to do better the next day. But if I reward them or do nothing, so if I come out and the guy has a terrible, terrible run, comes back in, and the instructor comes up to him and says, it's okay. Happens to the best of us. Or says, hey, you really did this really well. Forget about the things you screwed up. You did these really well. So anywhere from punishment to neutral to reward. Found that didn't matter. That pilot that had a shitty, shitty day almost always did better the next day, no matter what the instructor did. The same thing would happen if a pilot had an incredible day. If the pilot went out there and this was the best day of flying they ever had, he'd go out there and he'd say, that was fantastic. You did great. Do it again tomorrow. Well, basic reinforcement means he should be more likely to perform that same behavior again tomorrow. But invariably, that really good performance was followed by a less exciting performance the next day. We see this in sports, we see this in musical auditions and performances, and in dance routines, and in acting, and in everything. Largely because we all operate on this average. Your average, my average, there are different averages, but we all have our own average level of performance in a task. Sometimes we will be above that average. Right? The average isn't a constant. It's an average, a mean of all of these observations, some of which were above, some of which were below, and a lot were probably pretty close to the center. But those really extremely high or extremely low ones don't last. When I have a really good day flying, or I have a really bad day playing soccer, well, the next day, I'm unlikely to still be that extreme, and I'll be closer to the center, right? Because that was not my average. That's an unusual situation for me, and being closer to this point is really much more likely. And so this regression to the mean occurs all around us, and sometimes it can be a little bit hard to identify. So let's watch a real quick video on that that I think explains it perhaps even better than I did, if that's possible. And then we'll be done with this particular video. All right?
A basketball coach tells his statistician friend how confused he is because it almost always seems that 1. Whenever he congratulates a player after a great performance, he does worse next time. 2. Whenever he angrily criticizes a player after a poor performance, he does better next time. Does this mean he should stop congratulating players and only criticize them? The statistician laughs and tells him no, not really. In fact, the coach is describing the so-called regression to the mean, which is just a fancy way of saying that things even out over time whenever there's luck involved. Or chance, randomness, whatever you choose to call it. You see, in many cases, basketball games included, luck plays an important role. Sometimes you get lucky and play better than normal. Other times, bad luck makes you perform worse than usual. In both cases, you tend to move back to your mean, or if you will, average performance. He then tells the coach, 1. A player who performed remarkably better than usual was probably having a lucky day, and whether you congratulate him or not, he's likely to revert to his average performance after that. 2. A player you criticized because he did worse than usual probably had an unlucky day, and whether you criticize him or not, is likely to do better next time, climbing back to his average performance. Make sense?
That's it. That's it, right? Even my dog Lucy says this is easy. Let's see some math. So let's do it. Next lecture, math.